Excellent. Okay, nice to see everybody. I'm glad we haven't scared everybody away. So let's see, in terms of announcements, things for beginning a lecture and so on, pretty much same as always. Let's see, hopefully you all took your quiz sometime last Thursday or Friday. For those of you who sent me a panicked email on Sunday, the good news, well, the bad news is I'm not going to let you take it late. The good news is that we drop your lowest quiz score, and the quiz scores cumulatively through the whole semester are like basically negligible for your course grade. These are just ways to keep you responsible. So hopefully you learned your lesson. Your first homework is due on Wednesday. You do recall this class does have some late days built into your homeworks. They're additive and they're in the 24-hour cycle, and we are rigid and unforgiving if you miss the 8 p.m. deadline. The 8:01 p.m. is a 24-hour. You might as well turn it in 8 p.m. the next day. I don't negotiate. So that's everything I can think of on the announcement side. This class, again, pretty straightforward. There's, quizzes, homeworks, exams. Any questions? Yes.
Just like maybe this wasn't super clear on all the quizzes because they're 24 hours. We're not going to be like on a 48-hour shift looking necessarily at the answer on any given window that you can take the quiz. So just like as heads up, like the quiz is sort of taken on your own. We might post a question, but we might not get to that question before you finish the quiz.
That's right. And if it turns out that there's a mistake on one of the quiz questions, like our bad, I don't think there was this week, obviously we'll just give you all credit for that question and move on. These things happen. All right, any else to share? Comments, questions? Like cute recipes? Favorite Instagram posts? Nothing? Okay, fine. So today in lecture, we're going to continue our discussion of everybody's favorite everybody's favorite numerical problem, which is the least squares problem. And this is basically an extension of the linear algebra that we've all known and loved for many years. Essentially, the idea here is that I want to solve AX equals B, but for whatever reason, either like my matrix A is inaccurate or I just have too many rows, I don't expect to be able to solve this problem to 1,000% precision, even if I have the world's best number system. So instead, the best I can do is like AX squiggly equals B. And what we decided was that, well, at the very least, we can minimize the residual, right? Remember, residual is just the thing inside of the norm there, which is basically saying, like, find me the x so that AX is closest to B, at least in the L2 norm, right? And in lecture last time, we derived this system of equations at the bottom of the slide here, which is probably the most famous system of equations out there. Does anybody remember the name of this thing? A transpose AX equals A transpose B? Yes. The normal equations, yes, named after Jean-Pierre Normal. No, I think that's wrong. I have no idea where it comes from. Every year I intend to look it up and I forget. But in any event, the normal equations, A transpose AX equals A transpose B, is sort of the first example in this course of a thing that we do a lot of. And I think actually it has a lot of parallels with like undergrad style computer science theory, where like I feel like in CS theory, you basically only learn how to like solve one or two problems or like prove that one or two problems doesn't have a solution. And then you spend a lot of time doing reductions, right? Like showing that like, oh, if I could solve this thing, then I could also solve this thing. And in that universe, typically it's a negative result. Like, oh, if I could do this, then I could also do traveling salesman problem, and that's bad news. In this course, it's more of a positive thing, right? Like we started with the least squares problem, which somehow looks different than linear algebra, the way that we presented it from LU factorization perspective. But essentially, by deriving the normal equations, we have shown that if we have machinery for solving linear system of equation, then we can use that machinery for also solving least squares problem by basically inputting the matrix A transpose A instead of the matrix A when we do LU. Does that make sense? Okay. So that's our theme so far. And the good news is that like basically my point here is once you have a piece of code for solving linear systems of equations, the world is your oyster. You can do so many magical, beautiful things that you could not do before. And that includes least squares problems. So at least like, high school level statisticians are very satisfied with the things you can do to help them out. Now, I think there's a reasonable question here. I think, because, and so do many mathematicians over the last like 100, 200 years, which is as follows. So how will we solve the normal equations using the machinery we've developed so far in this course? Well, I think a totally reasonable thing Remember, again, we want to solve normal equations. So A transpose A, X equals A transpose B. I think in today's lecture, we're going to call this matrix C, just for fun. Because essentially, I don't want to say we're solving AX equals B because we're going to have confusion over like which one is which. But in any event, what might I do? Well, I could factor, right? I could do A transpose A equals LU from the machinery that we had before. And then I could write X is equal to U inverse L inverse B. And I want to be absolutely clear. We write formulas like this. Did I get in the right order? I did. We write formulas like this in this course all the time. Is this the way, like in math, like should I like calculate the inverse of U, the inverse of L, and then multiply them all together? I see heads shaking. Yeah, that's absolutely right. I gave you an efficient algorithm in our last lecture for solving an equation like Lx equals B, so like B is on the right-hand side. Remember, this is forward as the substitution. And so this is really just shorthand, right? This is saying like on the computer, essentially solving the linear system is not equivalent to computing the inverse of the matrix. And so we should really do the former. Okay, so this is a perfectly reasonable story, and indeed you can code it up today. You can load up, MATLAB, the superior programming language, implement these formulas, and then life is good. However, I would argue that like somehow spiritually this feels wrong. And why is that? Well, let's take a look at this matrix A transpose A. This matrix is super nice. Do you see that? In particular, what is the transpose of this thing? Itself, right? It's a symmetric matrix. But on the right-hand side, what have I done? I've written it in this format, which is like not obviously symmetric. I can certainly do this. That's perfectly fine, right? Like there's nothing in our previous lecture that said that LU factorization doesn't work for symmetric matrices, but somehow it feels wrong. Like there was nice structure here, and I sort of blew it up when I wrote down. Right? Similarly, A transpose A has a second property, which is really nice. And so in general, I'm going to make a matrix M, and let's say that I call it A transpose A. I'm only going to do this because like really it's going to be enough to have access to the elements of M. I don't really need access to A for now. Okay? Now let's say that I take some vector. You probably remember this from your algebra class, but I feel like a lot of these properties were introduced kind of abstractly, but they're actually like totally reasonable. Let's say that I take some generic vector X, and I compute X transpose times M times X. Okay, so let's expand this expression. What am I going to get? Well, this is, of course, X transpose A transpose A X. Okay, and remember that products of transpose is the transpose of the products of the transpose of the. I'm sorry, I started that sentence without like a good landing pad. But basically, I see two things that are transposed multiplied together. And so that suggests to me that I can couple them and flip the order, right? In particular, I can use a property that's easier to write down than say in words, apparently, which is that this is equal to AX transpose times AX. Remember, this is the rule. Like if I take two things and I multiply them together and I transpose, that is the same thing as flipping the order and transposing them one by one. Okay. So from lecture one, this is screaming out to us. What is this thing? Yes. Inner product. Or like in college algebra, another phrase for it. Rhymes with snot product. Yes, thank you. Dot product. Okay. So in particular, this is AX dot product AX. Or in an even nicer form, this is the norm of AX squared. What do we know about norms? Well, one thing we know is they can't be negative. Right? So this number is greater than or equal to 0. Okay? So basically, what I want to emphasize is that this matrix, this innocent looking M that comes up all the time in least squares problems. In fact, we're going to show it's kind of an if and only if, that like all matrices that have these two products can be factored this way. There are properties of them. It has two properties that are super nice and super helpful for solving linear system equations. One is that it's symmetric, and the other is that for any x, x transpose mx is greater than or equal to 0. And that's because kind of hiding inside of this matrix is some notion of a norm, right? Now from this factorization, neither of those properties is obvious, and that's because like they don't have to be true generically speaking. Yes.
A couple of questions. Are you saying that like the matrix product A transpose A is symmetric, or that A is symmetric?
A transpose A.
And then what are the like underlying assumptions of A that make that true? That what you're assuming here, is it just always?
Yeah. So the question was like, what about A makes A transpose A symmetric? The answer is nothing. Let's prove it real quick. So A transpose A transpose. Remember that the transpose of a product is the product of the transposes and the flip the word. So we get A transpose times A transpose transpose, which is A transpose A. So I showed that this matrix is equal to transpose, and hence it's symmetric. So no properties.
And then the other quick question: when you wrote down X equals even first L and first E, should there be an A transpose in front of B? Just based on like.
Oh, sure. Yeah, I'm sorry. I guess specifically for this linear system, you're right. Yeah, that's a reason. Okay, so I was thinking just generically for solving the system. Good question. Any other mistakes your instructor made? They're inevitable. They're going to happen a lot. Okay. So hopefully you get the point. But like essentially the normal equations, they're super important and super special. We absolutely love them. However, for this specific problem, it feels like there's structure we haven't taken advantage of. And in general, this is a theme in numerical analysis. You kind of derive the most generic algorithm first, and then you say, well, for a big class of problems, I could solve them with this algorithm, but I know a little bit more. And maybe I can use that information to come up with algorithms that are more numerically stable or efficient or whatever. And so we're going to see that as an example today. I should note that this isn't the only structure that shows up in linear system equations you can leverage. I'll mention a few other ones at the end of the lecture today. Okay. Incidentally, in our previous lecture, I mentioned we go through some examples of least squares problems, in particular one for image alignment. I think I was just looking at the lectures and we're a little bit behind schedule. So what we're going to do is punt on this example. It's in detail in the textbook. And if we have time at the end of lecture, we can go through it, okay? And of course, you can all come to office hours and hang out, which is like what I really want. It's like friends and it's lonely. And if you do that, I can also go through this in excruciating. Okay. So essentially, there's two examples in the book that both kind of start with the least squares problem, end up in the normal equations, and you should give them a read. Especially, I think this one is useful for testing your how'd that happen? For testing your understanding of the abstraction here, because the unknown in this problem is a matrix, and that feels wrong. And so you should kind of understand that, like, essentially the thing inside of the least squares problem is still linear. It's just linear in that matrix instead of the vector. And so the least squares problem still applies. It just takes a little more work to kind of massage it into that form. Any questions so far? Yes.
I didn't understand where did you go with this argument in the code over here. We wrote some things and then we said, oh, the norm is greater than 0, but what's the conclusion of all that?
What's the conclusion? The conclusion is that this matrix, M, which I've defined to be A transpose A, has a lot of nice properties that a generic matrix does not. And essentially what we're going to do is see if we can cook up algorithms for solving linear systems that leverage those properties. So they don't work for a generic matrix, but they do work for this guy. Yeah. Okay, any other questions? Fabulous. Okay, so we're going to skip these for now. We can come back to it if we have time. So the theme for today is to think about linear systems that are structured, to go back to the question we just had. Like Gaussian elimination and LU factorization can solve all of the example problems and more. However, it is not obvious that those are the best algorithms for solving these systems. Right? We haven't actually shown that. We've shown that it is effective, runs in polynomial time, so that's fine. But we haven't shown that there's not some faster or more numerically stable technique. Right? So, oh man, I'm struggling with these microphones today. I know this is weird, but the lecture video for this class, at least like I couldn't read the board, so I figured having a backup was better. Right, so in any event, once again now with a microphone, we have shown that we can solve all linear systems, but we haven't shown whether we can do better if there's more structure that we know. There's going to be a lot of other structures we can talk about. For example, sparsity, or on your homework, you work through like a very structured example, which is tridiagonal matrices. And again, I think the takeaway from that homework problem is once you know a little more about your matrix, you can come up with faster algorithms in that case than for the generic case. Okay? All right. So today, we're going to focus on the specific structure of positive definiteness. We'll also briefly mention sparse linear solvers. You could teach an entire course on sparse linear algebra. Sadly, we don't have time to do that. I would love to someday because those algorithms are super cool. And they look more like discrete algorithms than like numerical ones. But I'll at least kind of mention the kind of things that go into designing algorithms for sparse linear systems. When I say sparse, I mean like matrices that are mostly zero. Okay, so basically our lecture so far says that there's one ridiculously important matrix. And essentially what we've shown on the board, at least informally, is that that matrix has a few properties. Right? One is that, for some reason, by the way, I keep swapping between like B and M, and I think there'll be a C later, but hopefully we'll keep it straight. A transpose A, as a matrix, has two properties that are super important, hella important. One is that it is symmetric, right, which we've proven here. Yeah, thank you for keeping me honest. The other is that it is positive semi-definite, meaning that X transpose MX is greater than or equal to 0 for all X. Now, there's a second property which is related to this called positive definite. The difference between semi-definite and definite is if X is non-zero, then this norm is strictly greater than or equal to 0. One thing that'll let you guys check at home is so long as the columns of B are linearly independent, you get that second property for free. So in other words, like, as long as your least squares problem, for example, in A transpose A has a unique solution, life is good. Okay, I think in the textbook we worked that out in detail. It's just another kind of linear algebra exercise. Okay, any questions about these two definitions or how they relate to least squares? So here's kind of a fun thing that we're going to prove in lecture today. We'll talk about it a bit philosophically. I'm going to give you like kind of a spoiler alert now, and then we're going to go through the details and show that it's true. Essentially, our goal is going to be to show like some version of a converse of this property. So far, we've shown that if a matrix happens to be equal to A transpose A for some A, then it satisfies these two properties on the board. We're going to actually show the converse today, which is to say, suppose, oh man, I hate this board. Suppose that M is symmetric and positive, well, in class we're going to show definite. Semi-definite turns out to be sufficient. Then we're going to prove the reverse, that essentially there exists an L so that M equals L transpose. Right? In fact, that L is going to be non-unique. We're going to add some structure to L, namely that it's lower triangular. So in some sense, there's like an if and only if. And I think this is a really important point kind of spiritually, that like, I think in undergrad linear algebra class, you define these two properties like symmetric and positive definite, and we all like happily nod and say like, oh, that's fun. I love that for you to the math professor. The reality is these are very natural properties. And essentially what they're saying is even if you got a matrix that was SPD and you didn't know, by the way, SPD is symmetric positive definite, sometimes PSD. If somebody just handed you that matrix and told you it was PSD, but didn't tell you where it came from, secretly you knew it came from a least squares problem. Right? This is an if and only if. Yes? Positive semi-definite. Oh, yeah, sure. So P, D, S, P, whatever. Just put the letters in. Yeah, thank you. I'm going to say a lot of things that are wrong because speaking is hard. No, I'm giving you a hard time. That's absolutely right. In fact, actually, this is also true for positive definite matrices, but I think our proof technically will divide by 0 somewhere, so there's a little more work you'd have to do to justify that. As an extreme example, the 0 matrix clearly satisfies a factorization of this form. Anybody want to give it to me? Yes. That's right. Yeah, the 0 matrix is equal to 0 times 0, both of which also are lower triangular. So I guess, in fact, it's also the Cholesky factorization. Okay. So another question is, how do we get there? And so far, basically, the only sledgehammer that we have in this course is Gaussian elimination. But unfortunately for us, Gaussian elimination doesn't quite lead us to the right end, as I kind of mentioned on the upper board, right? Like, we end up with this LU process, and we're doing so by pre-multiplying by the same matrix, right? But essentially, even if I start with a symmetric matrix, if I pre-multiply it by anything, even if it's symmetric, by the way, the product no longer has to be symmetric, right? So somehow, we immediately destroy that structure in our algorithm. Does that make sense? And so what we're going to do today is we're going to do something really, really sneaky. And this is like such a clever proof. Like this Cholesky guy is really onto something. Essentially, what we're going to do is we're going to start with one step of Gaussian elimination. That's going to make our matrix asymmetric, right? And it's going to do so by the following, right? So what did we do in Gaussian elimination? We start with some matrix, and then we pre-multiply by some elimination matrix. Sadly, this product is no longer symmetric. What do you think we're going to do? Yes? Yeah, so we want to like maybe put something over here to maintain symmetry. To be precise, we probably don't want to invert it because we're not looking for inverse, but we're looking for transpose. So we're going to do, oops, not that. We're going to kind of ask this question, which is like, well, what happens if we just post-multiply by the same elimination matrix, right? And I think you could very reasonably ask. And in some sense, let's think about why we do that. I'm doing this kind of pictorially first because I think it's easy to get lost in the proof. And as we've seen, your instructor is likely to get it wrong anyway. So we're going to like draw some pictures and understand why this is kind of a reasonable thing, and then go back and justify it more formally. So let's say that this is our matrix M. You know, we've got this usual kind of like football style diagram, you know, like all the players on the field. I have no idea how football works. I don't know. I'm sorry. It's not really my area of expertise. I know this is shocking to you guys. Okay, so I pre-multiply by my elimination matrix. Remember what that does in our kind of pictorial picture is at the very least, it's going to put zeros here. In fact, by the way, if we don't use that scale thing, which today we're going to choose a slightly different scaling, then maybe we just have some unknown value instead of a 1 there. That's not a big deal. Well, remember when I started with my symmetric matrix, if I look at this vector and this vector, what do I know in the symmetric case? These are transposes of one another, right? So essentially what's going to end up happening is when I post-multiply by E transpose, I'm going to kill these elements. And when I pre-multiply, I'm going to kill those ones. And now now I have a matrix which has got some element, a bunch of zeros here, and then a bunch of stuff down there, right? And now I can kind of proceed recursively and like keep forward substituting. You guys understand the sort of pictorial version of our proof? I promise we're going to fill in details, but I just want to make it clear because at the end of the day, even if you get totally lost in the indices, I think this is a totally reasonable theorem from like 100 miles away. Okay, so that's going to be our goal. So now we do the terrible calculation that I hate, and we're going to get it wrong, give up halfway through lecture, and send you home, and you can do it yourselves. Okay. So for now, what we're going to do, yeah, see, I've switched letters again. I apologize. We're going to solve a linear system of equations, Cx equals D. And now we're going to make this additional assumption that C is positive definite. Okay? And what we're going to see is that we can basically use elimination matrices in this clever symmetrized way to get this new factorization called Cholesky. By the way, Cholesky is just a special case of LU, right? Where U is the transpose of L. Okay. Is it okay if I erase this? I'm already out of space. Okay. So here's going to be what we do. And by the way, this is a good introduction to like sort of common proof strategy that I think we'll use a lot in this course, which is this sort of blockwise linear algebra. So the idea is that like C is some big generic n by n matrix. We're going to isolate the first row and column of C, and then we're just going to use C squiggle as a placeholder for like all the stuff that we don't care about yet. Cool? So in particular, I really wish my notes wouldn't fall asleep. This is the one disadvantage of this thing. Okay, right. So I have an n by n matrix C. And in general, I can write it in the following fashion, which is I'm going to take the very first element, I'm going to write it C11. And I'm going to take the remainder of the first column, and I'm just going to give it a name. I'm going to call it V, okay? Now, because I know that C is symmetric, I know that the upper block of this thing is V transpose. By the way, I'm going to be sloppy about this vector sign, but for now I'll write it because I want you to remember like what's a scalar and what's a vector. And now I'm going to take the lower right of this matrix, and I'm just going to call it C tilde. And my goal is going to be to show that if I conjugate, just fancy linear algebra word for pre and post multiply by elimination matrix, then essentially I'm going to kill the V's. That make sense? Okay. So in order to do this, what we're going to do is we're going to define an elimination matrix. We're going to work through the product. We're going to do a little bit of ugly algebra. And then to make our life worse, we're going to multiply a second time on the right-hand side and show that really beautiful thing happens. Okay? So we're going to take a slight shortcut here, which is to think a little bit about our elimination matrices. So remember what our elimination matrices look like so far. Essentially, if you kind of recall the formula we had before, it was like the identity, and then we had like a single non-zero element. Like, let's say that we're in the very first step of Gaussian elimination. So it's like somewhere in the first column here, like that, right? And this value is basically the amount that I scale the first row to forward substitute. You guys remember this? So one thing that you can justify, quite easily, by the way, just by multiplying these things together, is let's say that I look at all the forward substitution steps in the first, like that take care of the first column of my matrix, and I multiply them all together, then essentially you can write this in a compressed way, which is to just take those non-zero values and write them down the first column of this matrix. Okay, I'll let you justify that at home. But essentially, it's very straightforward. If you just take the formula for the elimination matrices and you multiply them together, you'll see that it looks like this. Does that make sense? Like, essentially, all I'm saying is that, like, I can take this first row and copy it down to all the other rows at once rather than one at a time. Yes?
I'm a little just confused by the statement.
No problem.
Are you saying that like you can eliminate each entry all at the same time, or that?
That's right. So like essentially the way that we defined this algorithm before, right, we had some matrix, whatever it was, and we used one elimination matrix per element. So we like used one to zero this guy out, and then a second one to zero that guy out. All I'm suggesting is you can kind of compress all those into a single elimination matrix by taking all those values and putting them down the first column.
Just like multiplying pages.
Yeah, and you'll see it just algebraically. If you take the formula for elimination matrix and multiply them together, what's going to happen is the dot product between different standard basis vectors is zero, which is essentially what's happening here. Yes?
This also works across columns, right?
Across what?
Across multiple columns.
It actually does not work across multiple columns. If it did, then it would be a little bit too easy to compute the inverse of a matrix, right? We'll think about it a little bit. Yeah. But it certainly works for one. Okay. Have I managed to lose all you guys so far by making one sloppy math step? Oh, you're so agreeable. Ah, yes. No problem. Here, why don't we just write it out? It's okay. So here's my basic point. So remember that each elimination matrix takes the form identity plus some constant times EI, EJ transpose like that, right? So in forward substitution, the i's are bigger than the j's, and there's basically one of them for each row, right? So let's say that I have another one, E prime, equals identity plus some other, I don't know, D. I guess it'll be EK, EJ transpose like that. Right, because remember, they're both borrowing the first, so in this case, like J is equal to 1, and then like I and K are like the forward substitution rows, right? So if I multiply these things together, prime times E, what am I going to get? By the way, I'm doing this live, so like there's like good probability we're going to try this. I'll get confused and then make you even unhappier than we started. Okay, so I have I plus C EI EJ transpose times, oh, I already got it wrong. E D E, oh no. Okay, sorry, I just got the order wrong. And then we have I plus C EI EJ transpose. Have I managed to copy things correctly this time? Okay, so what are we going to do? We're going to FOIL, yeah? Okay, so the product of the identity in itself is what? Identity. One more time for the people in the back. Thank you. Please, wake up, guys. Okay, identity. Then we have identity times this thing, right? So you're going to have C, E, I, E, J transpose. Then identity times this guy, D, E, K, E, J transpose, right? And now take a look at what's going to happen. You have C times D, that's fine. We have EK, EJ transpose EI. Yeah? So this is, notice hiding inside of here. In fact, we can just write it out. Sorry, I'm being lazy. CD, so we have EK, EJ transpose, EI, EJ transpose. Yeah? Let me parenthesize it like this. This is the dot product between two different standard basis vectors. So what is that value? You know, that gesture is very rude in some parts of the world. No, I'm just making a joke. I have no idea. This is, yeah, that's absolutely right. This is 0. So take a look at what we did. Essentially, my point here is that I can now take the C and the D and put them in the same column of my elimination matrix. I've just compressed 2 into 1. Okay? Sorry, I should have just done that to begin with instead of waving my arms around. Okay. So to put it differently, our forward elimination matrix takes this form. Now, the square root in the corner, that part is new. We're going to come back to that in a second. But essentially, my point is that we have a bunch of zeros except for some element in the upper left of our elimination matrix. We've got identity in the lower block, and then a bunch of values. We don't know what they are, but we do know they're numbers in the first column. Okay? Now, I've done a sneaky thing, and this is sort of an anticipation of the calculation that I'm about to do. I'm going to make a slight edit to my elimination matrix, which I can certainly do, which is I'm just going to choose the upper left element to be 1 over the square root of C11. This is kind of like equivalent to taking my problem and scaling it by a diagonal matrix. And what we're going to see is that makes our algebra a lot easier. Now, you should immediately, because I know you're all picky math students, especially like in this part of the room today. What should be the picky math kid question here? Yeah.
What if C11 is negative?
Yeah, what if C11's negative, right? Because then what? Like square root isn't even a thing. Yeah? So, anybody want to help me out? How can we Yeah, so we got the right vibes, right? Like we actually have some property for our matrix, which is positive definiteness, right? And that's going to help us out. So now the question is, how can we isolate C11 just to make sure that the square root isn't against the rules? It means like making mouth noises. Help me out. Yeah. So let's take my matrix and conjugate it by E1. Remember that E1 is just the vector 1, 0, 0, 0, 0, 0, 0, 0. What is this product? You want me to write it out? Okay, can we save some time? Yeah, this is just an expression for the very first element of my matrix. And by definition of positive definiteness, we know, in fact, not even greater than or equal. We know it's greater than 0. By the way, fun fact, a fun homework or exam problem I could ask is to prove that all diagonal elements of a positive definite matrix are positive, and I will let you think through how to prove that here. I'll give you a hint. You just change the index. Yeah. Okay? So the good news is that this elimination matrix is perfectly kosher, but we had to use the positive definite property to get there. Okay? So what do you think we're going to do? It's painful. I'm so sorry. We're just going to work out this product. Okay? And then this is actually very similar to the homework problem you guys have on tridiagonal matrices, which is like, don't think too hard, just start multiplying things. It would be my suggestion. It's like the kind of Toucan Sam approach to mathematics here. Does that phrase resonate? Probably not. You kids are too young. Right? You follow your nose. This is the toucan. This is Fruit Loops. Yes.
I just missed, what was the definition of R? Like, where does this E come from?
So E is the elimination matrix. So R is like the forward substitution. It's like the amount that I scale the first row to cancel out all the things underneath.
Okay, so you use like the compressed forward substitution.
Exactly, like the C and the D in our little derivation there. Okay, so we're going to calculate E times C because your instructor likes excruciating pain. Okay. So the first thing we're going to do is just copy our matrices down, which in my experience, in fact, looking at my notes, I have already gotten incorrect, so we're going live here. So this is 1 over the square root of C11. We've got an R down here. By the way, if C is n by n, what is the dimension of R, just for sanity? N minus 1 by 1. Okay. We got a 0 up here. And then an identity down there. And now we have C11. We got a V transpose. We got a V and a C tilde. Okay. So what's going to be our product? So let's see if we can do this, right? So we have 1 over the square root of C11 times C11. What's that going to be? Square root of C11, okay, plus 0. Oops, wait, that shouldn't be. I don't get to do that. Sorry. This isn't V. But it's still 0 because of the 0 there. Okay. We have 1 over the square root of C11 times V transpose plus 0 times C. Okay. We have C11 times R. Remember, this is a scalar plus V. And now we have, it's going to turn out not to matter, but just for completeness, we'll write it. So R V transpose plus C tilde. Cool? At this point, you guys are hopefully suitably suspicious of any calculation that I do in this class. But I've checked my notes, and they agree, which means like with 50% probability is correct. What can I say about this matrix? Can I say anything? Now remember that like I define E to be an elimination matrix, right? Elimination is the key word here. Yeah. That's exactly right. So to repeat our colleague here, we know that C11 times R plus V is equal to 0 because that is the definition of our elimination matrix. Remember our sort of like schematic of forward substitution is in my first elimination step, I kill everything in the first column. Does that make sense? In fact, by the way, this is one way to derive an algorithm for LU factorization is to just kind of go through these steps. Okay. What do you think we're going to do next? Post multiply. Okay. The good news is that like we at least managed to get 1 0 in there, so like it could be more painful, yeah? Okay. You can see why I wanted to like punt on some of the other things that we talked about today, because this is a calculation that I think is worth doing kind of slowly. Okay, so what are we going to do? We're going to compute E, C, E transpose like that. The good news for us is we already have an expression for E times C, right? So that's square root of C11. We got a 0 down there. We have V transpose divided by the square root of C11. And we've got, oh, yeah, that's, wait, is that right? No, I'm sorry. Oh, yeah, that's right. I'm sorry. RV transpose plus C tilde. Right, so I just copied our form from the previous one and then quickly questioned all of my hopes and dreams while I do a bunch of math in front of 1 million students. Okay, but now I have to post multiply by E transpose, which conveniently I've written down. So what is E transpose? The upper left element is still 1 over the square root C11. And now we got to be careful how we flip this thing. We've got an R transpose up here, a 0 down there, and an identity. Okay. So it's important not to think here, right? Like our goal is to just like write a bunch of stuff. So sadly, we got to actually do this product. All right. So what is the upper left element? Well, we've got a square root of C11 there and a 1 over the square root of C11 there. Now you can see why I sneakily inserted that in our elimination matrix. So I get a 1 plus 0, yeah. Our next one is kind of ugly, right? We have a square root of C11 R transpose plus V transpose divided by the square root of C11. That feels kind of gross. We'll come back to that in a second. Okay. What do we have on the bottom left? Well, we have 0 plus 0. And on the bottom right, we have 0 plus R V transpose plus C tilde. Everybody with me so far? Nods, acknowledgement, literally like signs of life, please. Thank you. Okay. Now, our goal was to end up with something that looked a lot less ugly than this. So I feel like I failed. The usual hands go up. Yes. Oh, brilliant. Brilliant suggestion. I forgot your name. I'm so sorry. Alicia. Alicia has exactly the right idea. In fact, I'm going to give you two different proofs that this value is equal to 0. All right, one proof, which is exactly right, is if we look at this expression here. Remember, we already argued that C11 times R plus B is equal to 0. Take a look at this expression here. If I scale the whole thing by the square root of C11, well, that's C11 times R plus B. So we know it's equal to 0. So just algebraically, we've already actually shown that this is a 0 value. Can anybody give me an even sneakier proof? Yes?
Prove that thing is also symmetric.
That's right. So C is symmetric. So it's pretty clear that EC, E transpose is a symmetric matrix, right? We showed that this element is equal to 0. So we kind of know that the upper right has to be equal to 0 because it's symmetric and we already have value for the lower left. Yeah? So either of those proofs is perfectly valid. Yeah? So at the end of the day, what did we show? We showed that this product EC, E transpose is equal to 1, 0, 0, and then other stuff. The other stuff kind of doesn't matter. Yes?
So if we were to supposedly continue doing this, do we need to show that the bottom right is still positive semi-definite?
Do we need to show that the bottom right is still positive semi-definite? You do, and I'll let that be an exercise to the reader. Yeah. Essentially, what you can show is any product of this form is still positive definite if C is positive definite. Yeah. It's actually just a simple extension of our proof. Yeah. So basically, what did we do? We showed that if we just are sneaky and we post-multiply our matrix by the same elimination matrix we did on the left, then now we get in this nice form where we killed not only the first column, but also the first row. Isn't that cool? So basically what we can do is apply that construction recursively, and that's what's going to lead us to the Cholesky factorization. Okay? Now, stepping back in our proof, we should be really careful here. Does this proof apply to all matrices? Absolutely not. Like if you go back into our derivation, notice that we use the positive definite property to show that, like in this case, C11 has a square root, right? And more generally, we're going to need that like the upper left element of this thing, whatever it is, has a square root. Moreover, we use symmetry in order to justify that this thing was equal to 0. Yeah? And in fact, you might think like, oh, well, the algebraic argument didn't use it, but it kind of did if you go back and look. Okay? And so this is the kind of example of the thing that we can do in this class. Like if we know our matrix is positive, definite, and symmetric, we can come up with a better factorization than the generic LU case. Right? So in particular, what we've essentially justified by just applying this argument one by one, like you could basically apply that argument now to this matrix, right? And basically for every elimination matrix applied to this guy, it's the same as elimination matrix applied to the big guy, just with like a 1 in the upper left. We've justified that we can write C as a special factorization, LL transpose. Cool? Now I have given you an algorithm for computing this. This is kind of suggestive of an algorithm, but it feels awfully inefficient. But we've at least shown that it exists, right? That's the first step. Yeah?
Can you just repeat that last statement about how you get L transpose?
Oh, absolutely. Yeah, so if I apply an elimination matrix to this guy, right? So let's call this like E squiggle, right? Then essentially that's equivalent to doing that, but like just leaving the upper left alone by making it 1, 0, 0, E squiggle. And that's sort of the inductive step that you'll use.
Does that yield like a diagonal matrix?
It does. But specifically, we've engineered our factorization to put a 1 here. Right, so it's going to yield a bunch of lower triangular things on the left and a bunch of upper triangular things on the right with an identity at the very end. Yeah. Fabulous. All right, so our goal for the next 40 minutes is to write the actual algorithm for computing Cholesky factorization. And the convenience here is that now that we know that it exists, we can use the form of the Cholesky factorization to actually reverse engineer the algorithm a little bit. By the way, for years, I've tried to come up with like a nice proof that does this all in one step. You can, but then you end up in like this kind of weird, like, you kind of secretly know where you're going, but like I'm not convinced that it's any better than just justifying this and then going back and coming up with an algorithm. Okay. So essentially what we're going to do to actually make an algorithm for computing Cholesky factorization is go through our calculation again and introduce more ugly indices. Get psyched. But in particular, essentially the strategy we're going to use is very similar to the strategy you should use on your homework for this tridiagonal matrix thing, which is you first convince yourself such a factorization should exist, and then you go back and say, well, if it exists, then I can just kind of write L as a big matrix of unknowns, like L11, L12, L13, and then write a formula for every element of the product, and then just kind of start matching them together. Okay, so let's see what that looks like. Oh no, did I give it away? I'm sorry. I guess I should swap these. I would bring a stool and use the upper half of these boards, but that somehow feels like admitting defeat. Okay. So here's what we're going to do. We're going to take a generic, so like so far we've justified that for any positive definite matrix C, it admits such a factorization. Now our next step is to come up with an algorithm for computing it. And the way we're going to do that is we're going to like laser focus on one row of L at a time and come up with a clever way to write a formula for that row and show that you can kind of apply it inductively. Okay? So in particular, sorry, there's even more ugly notation here. Here's what I'm going to do. I'm going to take a generic lower triangular matrix L, and I'm going to kind of isolate the kth row of this matrix. This is just notation. I can always do this. Okay? So in particular, what we're going to do is we're going to write it in the following kind of funny form. We've got L11. I've got some vector LK transpose. We've got LKK. This is the element on the diagonal. We've got L31, LK prime, which is like a vector of values, everything underneath the diagonal, and then L33, and a bunch of zeros. Okay, I want to be clear, I haven't done anything. This is just notation. You guys see that? So essentially what I did is I said, I'm going to focus in, this is row K, and then everything above it is just whatever, and everything below it is whatever, but I'm going to give it all names, okay? And similarly, by the way, this is column K. So as a sanity check, LKK is a scalar, right? LK prime is a vector, and how many elements does it have? K minus 1, right? Because it's everything below the diagonal, right? LK is also a vector with K minus 1 things. These are not equal to one another. This is a mistake I made in my notes. This is just a generic matrix. I can say nothing about it, but I do know that L11 and L33 are lower triangular. Everybody with me? I warned you this is ugly indices.
Why are they lower triangular?
Because L is lower triangular, and this is a block of the lower triangular matrix down the diagonal. Great question. Any others? I see confused faces. Yes?
So L2T is a row vector.
That's right, it's a row vector. This guy is a row vector. So again, I have isolated, like I have a big matrix. I've isolated a single row and column of this matrix. Schematically, it looks like that, right? So like now you can see like L33 is this piece, L31 is this piece, and so on, right? So this is just notation. Yes? Oh, yeah, the middle bottom entry here, I've just labeled it as LK prime. Might I suggest our oh. Yeah, you should use this on the board, sorry. It's a vector, not a matrix. My apologies. I'll fix it. Somebody remind me, I'll fix the slides. Okay. Have I managed to confuse you all yet? Because I can try harder. Yes?
Yeah, okay. Could you maybe give like a specific like example like of an actual matrix? Like I'm having trouble just like rounding it.
Sure. Yeah, that's fine. Yeah, and then I do want to get to the end of this proof, so we're gonna keep going. So let's say we have A, B, C, D, E, F, G, H, I. Okay? And let's say that K is equal to 2. All right? Then LKK is just the number E. In this case, not 2.7 on whatever. Okay? Notice it's upper triangular, so these are actually 0. Right? LK prime in this case would be just this thing, but in general would be like a vector this way. LK is like a vector that way. L31 is this matrix, and so on. Okay? Fabulous. All right. Good. Good, good, good. So you guys are lost in terrible notation. Fabulous. So now what we're going to do, sadly, is multiply L by L transpose. Yeah, you're like an unhappy face. I'm with you. And you don't even have to do it on the board like I do. Okay, so what is L transpose? Well, the first thing we have to do, sadly, is just copy the formula for L. L11, LK transpose, L310, LKK, LK prime, 0, 0, L3, 3, like that. Okay, now we have to transpose this whole darn thing. Lucky for you, I wrote it down in my notes. So we've got an L11 transpose. We know that underneath it is going to be 0, 0, right, because this is the transpose. Now we've got this LK goes up there. We've got LKK, like that, and another 0. L31 transpose, LK prime, and then L33 transpose. Okay, that's the hardest part of this proof. Yes? Cool. All right. So the good news for us is actually the proof only really needs the middle row. Now, sadly, like Cholesky didn't know this when he wrote this, so he probably had to do a pretty nasty calculation. But the good news for you is you have an accomplished instructor who has done the proof for you and can tell you that, in fact, all we're really going to need for our argument is going to be the middle row of this product. So in particular, what is this product going to equal? It's going to equal some number that I don't care about. Now, let's work out element 2, 1. We have LK transpose times LK plus LKK squared. Okay? Oh no, it closed my thing. I'm sorry? What? For LK prime. Oh, yeah. Thank you. Is that right? Yeah, that's right. Okay, so we have LK transpose times L11, or sorry, LK times L11 transpose, rather. Like that. Plus 0 plus 0. Good so far? Look here, not there. I know there's a typo. Okay. The third element, turns out we don't really care about. Lucky for you. The first element of the second column we don't really care about. Obviously, if you were to do this proof at home, you probably wouldn't know this in advance, so you'd actually do the whole product. But, you know, such is life. Okay, so now, what are we going to get? We have LK transpose times LK, which is just the norm of LK squared, plus LKK squared, like that. Okay? Cool? And the good news is we actually don't need anything else. Okay? Otherwise, this would be a really painful calculation. Yes. Thank you. All right. So here's the good news. At the end of the day, what do we know? We know that LL transpose is equal to C, right? So let's just give C similar elements, right? So we know that there's like a C 1, 1. We've got CK transpose, C3, 1, whatever, doesn't matter. CKK, CK prime, and then other elements. So all I'm doing here is giving similar notation to the matrix C. This is just indexing. You see that? So what do you think I'm going to do? I'll just set these two things equal to one another and read off some nice relationships. Cool? I promise the hardest part of our proof is done. Okay. Your faces are killing me today. Oh my gosh, this is just indexing, guys. Okay, stay with me. Okay. So, geez, you guys are like, you're like sharks in the water. You smell a mild amount of unconfidence from your instructor, and then suddenly it just all, you know, collapses here. Okay. So let's read off some relationships. So first, let's look at row 2, column 1. Yeah. And while we're at it, let's transpose it. And we're going to get a really nice relationship. L11 times LK is equal to CK. You guys agree? Cool. All right, relationship 2, we're going to get CKK is equal to LK norm squared plus LKK squared. Cool? This, I claim, is actually all you need to derive an algorithm for Cholesky factorization. Yeah, it looks shocked. You should be, because it's super cool you can do this. So here's what we're going to do. We're going to apply these formulas inductively. Like basically, we're going to go row by row of our matrix. And we're going to work out, like one row at a time, what the elements of L should be. Yeah? Okay. And basically, when we do that, we're going to have to keep in mind, like, what do we know and what do we not know? Like that kind of thing. Yeah? So, by the way, notice that this, whoa, almost fell, is the same as saying that LK is equal to L11 inverse times CK. Cool? Now notice, let's say that I were computing Cholesky factorization one row at a time. Okay? And now I'm working on row K. Notice that L11 of my matrix there is above row K. Do you see that? So that means that's actually, those are numbers that I know. Yeah? So notice I know L11, I know CK because I just read it off of my matrix. It's some vector of elements there. So I can obtain LK, like the first K minus 1 elements of the Kth row, the sentence hopefully parses, by solving this linear system of equations. And how much time should this take? N squared, right? Because this is a lower triangular matrix. In fact, K minus 1 squared if you're picky, but whatever. Yeah, does that make sense? So if I know the first K minus 1 rows of my matrix, I can get everything except the diagonal element of the Kth row by solving a triangular system of equations. Isn't that cool? Yes, on. Is L11 invertible? It had better be, or else your matrix is not positive definite. I'll let you think through that one. Everybody with me so far? Okay, so now I know everything in my Kth row except the diagonal element. But let's take a look at this expression. Well, notice that the diagonal element's sitting right there, right? So what we can do is say, okay, well, LKK, be a little bit careful, is equal to plus or minus the square root of CKK minus LK squared. By the way, on a different way to answer your question is like, well, if it weren't, then your matrix couldn't possibly be positive definite because every step that we've done here is just built on that assumption. Okay, so now we have a formula for the diagonal element up to sign. So one question remains, which is what sign do we choose? It turns out the answer is it doesn't matter. Why is that? Well, think about, remember my Cholesky factorization is like this, right? I could easily stick a diagonal matrix and then a diagonal matrix inverted like that. So I can put a bunch of plus or minuses ones there and they just cancel out. Yep. Like essentially, scaling every column here is the same as scaling every row by a sign. So it doesn't turn out to make a difference. In any event, I think the standard here is to just choose a positive number. Okay, so this is the algorithm for Cholesky factorization. It's really magical. Essentially what you do is you just make two observations, which is that you can get it sort of one row at a time by solving a linear a system of equations which is lower triangular, and then just writing a formula for the diagonal element. So you do triangular system, diagonal, triangular system, diagonal, triangular system, diagonal, and you fill in L one row at a time. Right? So really all this is doing is building on the code you already had for solving lower triangular matrices. Isn't that cool? I think it's a really beautiful technique. All right, I saw a hand over here, but it was in my peripheral vision. Yes?
Is this still overall O in Q?
That's a good question. Yeah, what's the runtime of this algorithm? So this thing is upper bounded by n squared, right? How many times do we do this? Well, we do this once per row, right? So indeed, this n squared times one more factor n. So this is n cubed times. So the timing of this algorithm is no faster, at least asymptotically, than LU factorization. I believe if you work through the details, it turns out there's a constant factor is a little lower for this one. But yeah, there's no free lunch here. Yes?
So if it's like asymptotically the same, why would we care to use this factorization over something like that?
That's a good question. So why bother? Totally reasonable question. There's one really obvious one. How much memory does it take to store the Cholesky factorization? well, 50% of the memory it takes to store LU, right? You only have half the matrix. Moreover, it's sort of structure preserving. So there's a lot of things, calculations we're going to do in this class that like are just nicer for symmetric matrices. And the second that you leave that space, things can go wrong. And so the good thing here that we're kind of looking forward is that this is a way to preserve that structure in a nice way. Yeah. On the other hand, by the way, if you guys are really picky, this is a numerical methods class. So last week we talked about CPUs as this model of computation that can add, subtract, divide, and multiply. Is that enough to implement this algorithm? I see some heads shaking. What's missing? Square root. That's absolutely right. So technically, we need a little bit more to implement this, which is a piece of code for taking square roots of numbers. We'll return to that when we talk about root finding problems. But I think it's a pretty safe assumption that like your programming language has a pretty reliable square root function. Yes?
How do we know that LKK is going to be real?
How do we know that LKK is going to be real? I think there's kind of a stupid argument, which is if it weren't, then our Cholesky factorization wouldn't exist, but we already proved that it exists. Yeah. That's why this proof is a little bit sneaky. Essentially, we did one argument to show that it exists, and then because of that argument, we know all the steps we wrote on the board are sort of kosher. Yeah. Okay, fabulous. So in any event, the good news here is for any symmetric positive definite matrix, we now have a way to factor it in this LL transpose thing. So I think a nice sort of philosophical point to come back to what we already talked about is that essentially anytime we have a positive definite matrix C, right, and we can always write it as C LL transpose. So even if we didn't know LL and transpose, just the fact that it's symmetric positive definite is enough for us to know that it admits such a factorization. That's what we showed. And so essentially, any time that you see a quadratic form of the form X transpose CX, secretly behind the scenes, this is the norm of LX squared, meaning that really this quadratic form is computing a norm of a vector in some rotated space. Okay, so I think that's the right way to think about symmetric positive definite matrices and quadratic forms. Like I think this shows up all the time in linear algebra class, but I think a little bit implicit is just that really these are just fancy dot product matrices. That's all they are. Doesn't that make sense? By the way, if you're like a differential equations person, you could say the same thing about elliptic operators, sort of like the fancy infinite dimensional version of the same story. Okay, so this is our first example of a structured matrix in linear algebra. And notice that just by kind of revisiting our LU factorization, we can come up with an algorithm which is a constant factor faster and uses half the memory. This also happens to be more numerically stable. Incidentally, there is a version of Cholesky factorization that doesn't require computing a square root. I'll let you guys read about this a little bit at home if you're curious. There's something called the LDLT. The T is really stands for transpose, but when people say it out loud, they say LDLT. Where essentially every time you take a square root in Cholesky, instead here you kind of just like stick that number along the diagonal. Right? Because the square root was just to engineer a 1 in the corner, but you didn't really have to do that, right? This algorithm, actually, because it doesn't compute a square root, can also work for some matrices that are not positive definite, which is kind of cool. Anyway, this is more of a, just like a fun fact than something you really need to know. However, actually, LDLT does not exist for all matrices. It like lives in some weird middle universe, which is why it's a little hard to talk about. In particular, in order to cover all matrices, you need to pivot, right? And we haven't done that here. Yes?
Just so we can LU solve that AX problem, but this one solves stuff.
Yeah, so let's recap a little bit. So LU can be used to solve any linear system of equation, right? I have A as long as it's square, right? So if I have AX equals B, I can factor A equals LU, and now I can get X through 2 lower triangular solves. If, in addition to that, I know that A is positive definite, so for example, it came from the normal equations, then I can factor with Cholesky. To get X is actually still the same procedure. You see that? It's still like a lower triangular and then upper triangular solve, or the other way around. It's just that those two matrices happen to be the same. Yeah. Okay, so in the last little bit of class here, I thought I would mention some other matrices that also have nice structure, because I want to make the point that like symmetric and positive definite is not the beginning and end of the story. There are like all kinds of nice matrices that have like nice stories to them. And essentially, when you're doing numerical linear algebra, I think a totally reasonable kind of prototyping thing to do is to start by just like calling a generic solver, you know, coding up your thing, making sure your system works, and then going back and like staring at your matrix really closely and asking, like, what else can I say about this thing? Right? So like positive definite is the most common example, but there are many others that allow you to solve these systems either faster or more in a more numerically stable fashion. And so I just wanted to briefly call them out. We don't have time in this class to derive specialized algorithm for every single one, but it's worth just being aware so that like when you're working with numerical linear algebra code at home, you don't call the generic piece of software if you don't need it. Okay? So I think the other example that's extremely common is sparsity. So let's give you an example. So let's say that I have a matrix. This is very common in differential equations. That's like maybe -1, 1, a -1, 2, -1, -1, 2, -1, and 2, -1, like that. Now, this matrix has how many non-zeros? Like roughly 3n, up to a few constants, right? Because there's a bunch of zeros down here, a bunch of zeros down there. However, it's not obvious how to use that fact in the algorithms that we've derived so far, right? Like for all we know, for example, if we had really bad luck, like let's say that this matrix were almost like that one, but then like some jerk stuck a 7 in the bottom row, then what's going to happen in the first step of forward elimination? Well, now I take this first row and I copy it down there, and suddenly now I have a non-zero there, right? And then what's going to happen? Well, now when I cancel that thing out using the next row, I'm going to add another non-zero here. This phenomenon is called infill, and it's really irritating. Essentially, the idea is if you go through the steps of Gaussian elimination in a sparse matrix, you can actually cook up counterexamples where by the end of just the forward substitution phase, the entire thing is dense. Yeah? So that's bad news. Yeah? I'll let you guys think about an example where that happens. That would be a fun homework problem. Yes? Doesn't really matter. The common one would have a negative one there. Yeah. Right, this would be the Neumann boundary condition for the one-dimensional Dirichlet equation. See, I can say fancy math words. Okay. Right, because like in principle, you would put the, I see what you're saying. No, yeah, you're right. That should be like that. Yeah. Turns out not to matter, right? Because you just have to flip the sign to your right-hand side. Okay. Good. So hopefully I've convinced you guys that like sparsity is another example of the kind of structure you might preserve in a linear solver. Notice, would it make sense to store a matrix like this as just a big grid, like an n by n grid of numbers? Probably not, right? So like for instance, a very common data structure would just store like I, J, value, like just a long list of row, column, value, right? Or there's all kinds of other cool sparse matrix formats out there that like store them, for example, in sort of a clever order to make matrix multiply easy. Yeah, it's really fun to read about this stuff. So here's, I mentioned some things that can happen. So like here's another example of sort of a generic matrix structure where the matrix is pretty good. And then as you carry out LU factorization, just because of these forward and backward substitution steps, in fact, actually, I put a bunch of zeros down the first column here. Let's say that there were non-zeros in the first column. I think that's actually easier to see. So I have this, by the way, is called an arrow-shaped matrix. I don't know where they occur in nature, but I feel like they show up a lot in math textbooks. What happens during forward substitution if all these zeros in the first column are non-zero? Well, remember, I take copies of the first row, and I start copying them down to cancel out that first column. And then suddenly, all of these zeros are gone. Right? And so essentially, the algorithm that we talked about for Gaussian elimination, it still works, so it'll run in n-cubed time, but it's not terribly efficient from the perspective of sparsity. And a reasonable question you might ask is, can I do better? Now, in this class, sadly, we don't have time to derive algorithms that solve sparse linear systems in great detail. By the way, like 2/3 of the way through this class, depending on how far we get, we can have a little vote on like the last couple lectures, like what topics, and this could be one of them. Sparse linear algebra is a super cool area. It's very combinatorial. It so somehow feels very different than what we've done so far. But essentially, one thing, if you're kind of curious to read more about these algorithms, they're a lot of fun. Here's an interesting thing. So let's say that I like permuted the rows and columns of this matrix to just stick that big non-zero row all the way at the end instead of the beginning, right? I can certainly do that, just swap the first and the last row. Now that infill actually is no longer a problem, at least during the forward substitution phase. Do you see that? I just swap the first and the last column, or row rather. And so like essentially, this is the kind of interesting observation. LU factorization depends on the ordering of the row in the column of the matrices, right? That's sort of why we can do all this pivoting stuff, right? Which means there's actually sort of a degree of freedom here. Like, as I do LU factorization, I can pivot strategically to avoid introducing non-zeros into my matrix. That's a bit different than pivoting for numerical stability, which is what we talked about so far, right? And so if you're curious to read more about structured linear algebra problems, yet another thing that we can do is to permute the rows and columns not to lead to numerical stability in the LU factorization, but rather to minimize infill. In fact, if you're like a discrete algorithms person, here's a really fun question you can ask. Can you, if I just give you the sparsity pattern of a matrix, like that kind of XO diagram that we've been using a lot, can you come up with the permutation of the rows and columns of the matrix that minimize the number of non-zero entries in the LU factorization? Does that sentence make sense? It sounds very fancy. Fun question. How many of us think this is like, you know, just like one of these things that go take an advanced algorithms class and they're going to tell me how to solve it? The answer is actually no. This is an NP-hard problem. So it's actually quite difficult to find the ideal permutation of a matrix from sparse linear algebra perspective. But there are some really effective heuristics out there. I think the sort of state-of-the-art one that most people use is something called approximate minimum degree ordering, which has to do with like looking at one of these matrices as a graph and then ordering it in some way that kind of lays the graphic out on a line, and that has something to do with the infill. But these are really beautiful techniques, and it's really cool because you have like one foot in numerical linear algebra and another one in like purely discrete graph algorithms. And so it's a really interesting combination that way. And so actually, what happens in a lot of sparse LU factorization codes is it happens in like 3 phases, which is kind of cool. So the first phase is purely combinatorial. It comes up with like a way to permute the rows and the columns to reduce infill, right? So it kind of like pre-multiplies and post-multiplies your matrix by a permutation. Then they do symbolic factorization, which actually goes through the steps of LU without any numbers. Like it just keeps track of like the list of forward and backward substitutions, which in this case is some kind of sparse list if you think about it, because now a lot of forward substitutions are just 0. And then a final stage is what they call numerical. And it's only in that last stage do you actually get the numbers. You just go through that process again, which is really interesting. So in a lot of cases in differential equations, you'll end up with a bunch of matrices with the same sparsity pattern, but the actual entries change. And so that's sort of optimized for that case. So like, for example, like Leticia, your TA, you might not know it, but you should look at her webpage. She works on these simulation problems with like squishy materials, right? Like these wobbly, jello-y flubber guys. Sorry, not flubber, that's copyrighted. Flying rubber characters. And as they do that, right, the matrices are coming from the dynamics of the physics problem, but they're also sort of assigned to the vertices and edges of a triangulated surface, or like a tetrahedral mesh. As long as the combinatorics of that mesh don't change, the sparsity pattern of the matrices she's working with remain the same, but the actual values change from step to step. And so that's an example where you might get some additional value out of separating out, sort of going through the motion of LU from actually doing the numerical thing. Okay, so anyway, this is just a preview into that universe. Another common one is something called a banded matrix. These are matrices that only have non-zeros in a band around the diagonal. On your homework, you'll work out tridiagonal, which is the simplest case of banded matrices. But you can actually work through the steps of LU factorization in general for matrices of this form. They come up a lot in differential equations. And they're really cool solvers for these kinds of things. In fact, if they're not only banded, but for example, they're circulant or cyclic, meaning that they have some really boring property, like every row is just a shift of the previous one, then there's an entire other class of techniques that one can use for these things. Does anybody know this from any of their other courses? Yeah. The signal processing is exactly right. It turns out that the Fourier transform is probably the right thing in this case. Anyway, this is all like, you know, in general in our lectures, I think what we'll do is take a numerical problem, convince ourselves it's solvable, talk about the applications, and work through a solution. And at the end of our discussion, we're also going to identify some other kind of frontiers of interesting advanced topics. Obviously, that's the phase that we're in here. So I just wanted to hint to you guys a few of those moving forward. Cool? All right, so that concludes our discussion of Cholesky factorization. We got 5 minutes left in class, so I'll give you a quick preview of what we're going to do next in 67350. which is going to be sort of the end of our dramatic arc when it comes to solving linear systems. And for now, we're going to come back to it when we talk about conjugate gradient algorithm. By the way, conjugate gradient algorithm is going to be cool, super cool, because what we're going to do is work on solving positive definite linear systems. And the way that we're going to derive our algorithm is by kind of gradient descent on expressions of this form. But then we're going to show that if we kind of parenthesize it the right way, we never actually need L. It's enough to just work with C. So we can kind of bypass actually doing Cholesky factorization. In any event, so our final thing we're going to talk about for linear systems here is sensitivity and conditioning. Remember, this goes back to what we talked about in the first couple lectures, which is, so far, our discussion of numerical linear algebra hasn't really considered the fact that we store these matrices in floating point, right? Like the algorithm that we wrote down for LU didn't really account for rounding in any fashion, right? And so one thing that we should do is at the very least get some high level notion of like how well conditioned these problems are to make sure that like when we run our Gaussian elimination code, we can actually trust what comes out, right? And so that's what we're going to consider in our next lecture. Namely, if I run Gaussian elimination, I'm probably going to get some x naught for which the norm of ax naught minus b is small, but not exactly 0, right? Because as I ran my algorithm, you know, I made some mistakes, some oopsies. That's you know, my bad. Double precision tends to do that. And now the question is like, if I measure that norm and it's small, can I be confident that x naught is pretty close to the solution of our problem? Yeah. Notice that that is precisely the definition of the difference between forward and backward error, to give a little bit of formalism to our discussion here. Yeah, so as sort of some recall from a few lectures ago, remember that backward error is the amount that a problem statement would have to change given an approximation of its solution. So in particular here, here's what we're going to solve, and we're going to really tackle in our next lecture in great detail, painful detail, which is as follows. Let's say that I run a linear solver, it gives me x, and it gives me b, and they're wrong. Then how much could I perturb my problem so that they were the right answer? Or the kind of forward version of this problem is as follows. If I perturb my matrix A and I perturb my matrix B, how much does x change? Notice if I solve one of those, I've kind of solved the other. They're kind of duals of one another. Okay? So this is going to be sort of a souped up version of one of your homework problems on the quadratic equation, right? We're going to do a giant Taylor series. And our goal is going to be to try to understand like how perturbations of A and B affect the solution of our problem, which in effect we're going to see depends on the eigenvalues of A. Oh no, spoiler alert. Yeah. So that's what we're going to go about next time. As a bit of a preview, what we're going to have to think about a bit is what does small actually mean? Here's where it matters. Notice that I've sneakily, so far in this class, every time we compute a norm, I've tried to remember to put a little subscript there. But now what we're going to find is that there's a lot of different norms we could use that give us different notions of vectors being small. Some of them are going to lead to condition numbers that are actually computable. Some of them are going to be kind of hard to work with. And so actually for linear systems of equations, for this proof, what we're going to see is when we use like L1 norm, L infinity norm, it's going to be fairly easy to work with the condition number. When we use L2 norm, it's going to be in terms of the singular values of A, which are like nice objects to think about, but like we haven't talked about how to actually compute them numerically. For all we know, it's hard. Yeah. So essentially, what we're going to talk about first is what is small. And of course, in order to do that, we have to go back to our functional analysis class and talk about how to measure lengths of things. So hopefully we've all, I'm doing a little bit of review now to basically set up our next lecture, since we have a bit of time. So what we're going to do is say that essentially, when our perturbations are small, what it means is that its norm is pretty close to 0 for some vector norm denoted by a double bar. But we're not going to plug in the actual double bar unless we actually have to, right? So we can do this axiomatically, right? So in general, things that measure length have the following 3 properties. Essentially, the length is 0 if and only if x is actually equal to 0. If I scale x by c, then the length also scales by the absolute value of c. And we have this third thing, which is a triangle inequality. Hopefully this is a review. I'm just rushing through to set up our next lecture. Okay. All right. The most common vector norm is the 2 norm, which is the square root of the sum of the squares. But in fact, there are many norms out there. So for example, one of the most common one is the p norm, which is the 1 over p power of the sum of the pth power of the elements. This thing satisfies, you should check this at home if you haven't seen it before, all the axioms for a norm so long as p is greater than or equal to 1. When p is equal to 1, this is the sum of the absolute values. This is a special norm called the taxicab norm. Okay, so maybe we'll pause there. Essentially, in our next lecture, what we're going to do is first we're going to argue that essentially if a problem is well-conditioned in any of these norms, it's well-conditioned in any other norm, which is kind of cool. This is not obvious from the definition of a norm. We're going to show that all norms are equivalent in Rn. This is not the case in functional analysis. Moreover, that's actually also true for matrix norms. And then finally, we're going to derive a really ugly formula that's going to tell us a lot about the conditioning of our problem in terms of perturbations of A and B. And that's going to be kind of where we drop off on the numerical linear algebra front. Okay? So with that, a reminder, please finish your homework. Don't forget, you also have a quiz on Thursday, Friday again this week, but that's for later. Come to office hours. There are many. Leticia, I think, has them today. I have them, and I think Mark has them tomorrow. There's more on Wednesday and even on Thursday. So with that, have a delightful Monday afternoon, and I will see you all soon.